Okay, so this week we'll be wrapping up the linkage mapping stuff as far as the renaming of the files and start getting into a little bit how to use R and QTL and some other stuff regarding R scripts. Let's see. Okay, so last week we had been we'd finished up looking at renaming the markers that come out of Lep-MAP3 because they come out in a list that references the marker order in earlier files. And we had been having a few issues with getting the last step to work. So I'm gonna show you guys that again. Okay, let me scroll. Okay, so if we remember, we started out with just rows F through whatever it goes to. Oops. Then we referenced the order file that gave us that we were able to use the concatenate function and the VLOOKUP function to get this list of physical chromosome and physical position based off of what this number is. And since these numbers all go in order, these numbers also somewhat go in order since it's referencing a list. And an easy way to check that we were not off by a couple numbers on something is to scroll down to the junction between two different linkage groups and make sure that it switches from, like in this case, a 14 to 5, right where it switches from the end of one linkage group to the beginning of another. So the 0 is at the same place as the change to chromosome 5. But we're not done at this step because this is still just the physical positions. And while this looks okay for like GBS or RAMP-seq markers, we do want the actual name of the SSR markers that are located within here. This example is for RAMP-seq, but it would go the same way in data sets that have SSR markers. So what we can do to go from these physical positions to these marker names would be copying the first, I think, 3 or 4 rows of a HapMap file. And then similarly to how we concatenated these physical position names, we similarly concatenated the physical position names or physical positions in the HapMap file, and then left the actual column with the file names. So these 2 columns are coming from a HapMap file. And then at this step, we would again be able to use the VLOOKUP function in Excel. We would want to look up this value that's in column E within the array of these 2 whole columns all the way to the bottom. The column index, which it's kind of small in here, but this is showing me an instruction of what I all need to write in this function. So the column index is just, okay, I don't know if I can click on it. The column index is just which one of these columns, or if there were more past that, you could select those 2. But which one of these columns I want to extract the cell information from. And since we want the names, we want to take the information from the second column. So I'll put a 2, and then the range lookup. If I put true, that would give us an approximate match if there isn't an exact match, but false only gives us an exact match, and it'll return an NA if there is no exact match. So I'll put false in there and then enter the function. But since we will be filling this down all the way across, all the way down the column, we want to keep the array that we selected exactly the same. So we can put the $signs in there to make it not shift along with the first object in this function. So now that we see for this, and it's pretty easy to check with the RAMP-seq names, From the physical position 14_257160, we get ramp-seq, chromosome, and then the exact same information. So we know that that is correct. And if I fill it down, it all looks very close. A few of these are a few numbers off, but if we look in this column, we see that the same thing is happening. And that's probably just because it's the ramp-seq data and it represents a range of physical positions rather than like a certain exact physical position. And that's just how it got named. But it looks correct. We can do the same thing to come up to a switch between the linkage group numbers to see if everything looks all right. Yep. 1622, 1622 on this side, 3_7 on this side, 3_7 on that side. So that all looks correct. And at this step, we would be able to start deleting some of our extra data. But first, because this is still a VLOOKUP function, and if we delete the information it's referencing, it won't have that anymore. We want to select the whole column, copy it, come up to the paste, and then paste values in order to get rid of the function and just keep the plain text within those columns. Now, when we click on it, the VLOOKUP function's gone, and we can safely delete these columns and this column, and we can put this data into the actual map and replace the numbers. And now we have the map information that goes along with the centimorgan positions for the actual linkage map.
So how many, just curious, how many markers from 14
14 has, let's see, 7 through, this is ramp-seq, so it'll be a little less, 7 through 118, so 111, I think, or 110. And that will be the largest linkage group.
How about 18?
Oh, I was gonna go to the bottom and see how many was in the smallest. We can go back up. 3, I'm not gonna do the subtraction on these. The smallest ramp-seq only has 44, which is kind of small. Chromosome 3 is kind of small to start with. But
Right, and 18, let me see 18. How many 18?
5, 7, 1, 8, 6, 13,
14,
18. Not too far. $18 is 73.
How about 15?
15 should be really low.
15 is technically
Sure.
not that, like, it's not smaller than I think 3 in terms of like physical base pairs, but it generally has lower marker coverage.
15 should be low. Low.
All 14. 14.
Number 3 is 44, right? That's the least number. Least amount of number.
15 has 46, no, 48, 47.
47. Okay. So chromosome 14 is still the largest. Okay.
Yep, and that's been my experience even in like ramp-seq 14.
You know why?
It just has a lot of markers. Let's see, we start pretty close to 0, so that's fairly representative. Let's see what it goes up to.
Well, SSR the same, 14. That's the most. Anybody knows why SSR on 14? There are a lot of markers.
Oh.
Yes.
Well, first of all, 14 does go up to like a pretty high
Number.
physical position, like I think 18 might be go up to like past 30. I mean like 30, what is this, 30 million base pairs. But 14 is showing up at like 29, I think is what it's showing up as.
So roughly, right now, we talk about SSR first. SSR, the reason why 14 and 18, because most of the markers is because these two chromosomes being studied a lot, disease resistance. So 14 is a pure disease. 18 is RBP3. Right, so those two. And then after that, well, don't know why, for GPS and RAMSEC also got a lot of markers.
Which they're just longer. I think like 5, let's see what 5 goes to. 5 only goes to like 23 or 25. It looks like 25 million base pairs. So that's, what is it, 3 or 4 million base pairs shorter. But any questions about converting
So you converting
the file names?
whatever the RAMSEC data from 1 to 19, and then figure that out into the actual linkage map or the chromosome, right?
At this point, we've just changed the numbered list that references a previous file into the true marker names for those positions on the map.
So how you know that originally chromosome 1 is chromosome 14, actual chromosome 14?
It's because when, here, I'll exit out of this. Open it back up. Okay. So when we
See, this is what I'm talking about. Yep.
we start with just this number that comes out of Lep-MAP. And this number references the original input file that we upload it to. And that file contains this, the position and chromosome of all of the markers, which that would generally be kind of enough for RAMP-seq and GBS if we weren't concerned with the true names, but
So
it's good practice to actually use the names, especially for SSR.
those numbers, that will correct me if I'm wrong. So those 14, whatever numbers, is that from original, genome sequencing on Pinot?
Yeah, those are the physical positions based on which it could be a different one if somebody for some reason used a different reference genome, but it and all the methods that I've read, everybody uses the Pinot.
I'm not so sure what they use, because we do have Norton genome sequence, but it's really bad, not a good one, okay? Available. That was done by Dr. Chu a long time ago, right? And he even tried to propose to do resequencing, but still quality is not that great. That's basically right after I arrived here, so nobody really uses that. So we'll see that. Yeah, I'm not so sure whether they genome sequence Norton or they genome sequence one of the S dividers.
Yeah, I'm not sure.
Dividers gene 2 try to do that. And I don't know actually what they did sequence.
Yeah, I know there's something of Vitis estivalis parentage in there that were in their genomes that they used for this, but I don't know exactly what it was.
So currently this set of data only RAMP-seq or you already combined?
This is just RAMP-seq. Yeah, I haven't made any, besides the preliminary, I haven't made any maps that combine RAMP-seq with SSR or RAMP-seq with GBS.
You did have the copy with the SSR.
I did a preliminary one, but for the cold hardiness stuff, we were keeping them separate for comparison. Okay. So that's essentially that. Additionally, I guess I should mention in this file, the linkage groups or chromosomes aren't actually numbered. You would just need to come in here and fill in, since we know it's 14, fill in 14s down until the 0, and so on and so forth for 5 and 14, which that's not anything complicated. Just type it in and fill it down.
These
Just like
files come from the output of MAP file or code file, the file called file.
All of the stuff from F and on comes from the output file that comes out of that .awk function. It's essentially the same information that's in the order file, but it's just been delimited for the genotypes, so it's easier to use. And then this stuff is coming from HapMap file. We extracted this column from the file call file that we input in. Okay. So now that we've looked at that, let's get back to the PowerPoint.
So I asked this question many times. So for the Shimperson cabinet over now, we also use, right?
Not yet.
I still, I can do it for the GVS markers and I can do it for the RAMP-seq markers. We still need to convert the SSR markers into VCF because right now they're not assigned a physical position, so I can't use it in a HapMap file.
But for the RAMP-seq per se, Shimperson cabinets over now, we do that.
We have the copy, right?
Yeah, we have the data. I don't know if I've actually ran the RAMP-seq map, but it wouldn't be hard to. Okay.
So roughly, how many markers there? You didn't, I mean, the
For the
map is not there yet,
RAMP-seq one?
right?
No, I can check.
This is the Shimperson cabinets over now.
Let's see, RAMP-seq. This one. Not that one. Let's see. All right, so we have 3 folders that contain all the genotyping stuff. I'm just getting into the CHCS and opening up the HapMap file. I think they have a HapMap file. They don't. They have a VCF file. I should have checked that. Okay, I'll open it in Tassel. Oops. And I'll open up the plain VCF. Okay, I guess I don't remember if I mentioned this, but a thing about VCF and HapMap files, they have to be sorted by physical position. If they're out of order, it won't open the file correctly, but there's a plugin in Tassel that will do it. And it tells us this: please use sort genotype file plugin first to correctly order the file. So we can do that. And that's in the data sort genotype file. And it just open that VCF file.
So plotting, you have to add every single time or up to you?
Once you do it once, you don't have to do it again. just a second. Let me see. So usually I'll just use the same name and then put underscore sorted. We want to keep that as, we'll keep it as a VCF. And then it uploads it and saves it, so we won't actually see it. We'll just have to open up the sorted file here, and then it should open. So there's 1,954 markers. I don't know how many of those are good. Let's do at least 100.
And how many genotypes?
There's
2 plates, right?
It's 3.
275 taxa,
3 plates?
Yeah, so we 273 from parent.
which it looks like this one was a lot better coverage because I filtered to exclude the markers that don't have at least 100 individuals genotyped. And it looks like it only dropped out about 20, maybe like 18
So it's
different
19,
markers.
36
Yeah,
markers.
yeah, 1936. All,
So that's pretty nice.
yeah, it looks like a few of them might be monomorphic.
So this one got 3 plates. That means 91 times 3, that's 273. How about GBS? We only have 2 plates.
For the,
GBS, we only have 2 plates.
we might,
That's 91 times 2, that's 182 only. Okay, so at least we have, so this is better, okay.
I will say I just filtered with the ramp-seq stuff with like a 10% minor allele frequency and 10% heterozygous proportion, and it does drop down to about 1,600, which I think is still a little better than the Norton bicarbonate
It's a good number.
stuff, I think. But I thought I was. Oh, there we go. I tried to open the CHCS GBS, which the initial file has like 217,000, which is more than the 60,000 of Norton by Cabernet Sauvignon. We'll filter with that stuff.
It's only 184.
Yeah, so it only has 184 individuals though.
So 184, is that 182 plus 2 parents?
Yes. It looks like it has the replicate, parent replicates already combined. Yeah, so that's a CHCS data. Okay. So, and yeah, obviously all this stuff we've talked about, I've been showing examples from the Norton by Cabernet Sauvignon population, but everything's transferable. That's just the population I've been working with. Okay, one other thing about maps is that just like how in Lep-MAP3, it doesn't give us chromosomes 1 through 19 in order, it just does largest to smallest. It doesn't have, it doesn't always start from the smallest end of the chromosome. And so for like final map purposes, we do have to reorient maps that start with the largest physical position end. And so obviously like the beginning and end don't really mean that much, but since everything is now aligned to like the P-Noir reference genome and stuff, it's good for comparison purposes if you're looking at other people's data to always have the maps oriented the same way. And so in order to flip those manually, we don't have to reorder, we don't have to do anything in Lep-MAP, we just have to manually reorder them. Like in the example here on the left, this is an example of an extremely short map. That's chromosome 8 in this example. And so we can see that the marker that starts the chromosome actually has a longer physical position than the marker that ends the chromosome. And we would actually want it flipped so that this marker has 0 centimorgans and this marker has the 17.2 centimorgans. In order to do that, all we have to do is like extract the difference between each of the markers' positions. So to go from 0 centimorgans to 1.9, that's a difference, like a gap spacing of 1.9 centimorgans. 1.9 to 5.4 is a distance of 3.5 centimorgans, and so on. 7.3 between these two, and between the last ones is 4.5. And what we would do is just reassign the true first marker a 0, even though it wasn't a 0 coming out of Lep-MAP. And then we would add all of these distances to each of the markers. So to go from 0 to the next one, we had a distance of 4.5. And so we would add 0 plus 4.5, which that equals 4.5. So this marker, the second to last marker, would now become 4.5 centimorgans instead of the 12.7. We would do that same thing, but always adding to what the previous marker's position is newly assigned. So now that this is 4.5, we would use 4.5 in the beginning of the addition at the next marker. So 4.5, which comes from down here, plus 7.3, which comes from the distance to the next marker. And so that would be 11.8. And then adding the distance to the next marker, 3.5. So we just add up all of them, the 4.5, 7.3, 3.5, which you could replace these first two with the 11.8, and that would equal 15.3. And that would be the new physical position of this second marker. And then finally, the last marker, if we add up all of these distances together, we get the 7.2. And we know that's correct because previously, the previous last marker in that chromosome had 17.2, and it is still 17.2 when we add it up. If we got a different number, there would be some error in the addition. It should always be the same total length, even after we reorient. So after we've reoriented the map on the right, the map would now look like this from 0 to 17.2. And at this point, we would be able to actually flip the map, and all you'd have to do is put this marker on top, this marker underneath. You can just copy and fill down. Any questions about reorienting the maps?
This usually happens.
You only have to do this at the end. You still, even in join map, you have to reorient stuff. A lot of times pre-GBS and pre-RAMP-seq stuff, some people wouldn't reorient the maps since it's harder to tell with the SSRs, but when you're doing the QTL analysis and describing things in terms of centimorgans, it's not descriptive if you're talking about a different end of that chromosome than somebody else.
But usually the SSR, the order, it seems to be really sequential. So
it's sequential, but if the SSR markers, if we said we had a QTL between 0 and 1.9, and in our map, it's this 12, 34, 0, 15. But on somebody else's map, the first marker is 15.021. Just because if we have a QTL from 1.9 and they have a QTL from 17.2 to 12.7, it would still be the same thing, even though the centimorgans look different. And that would be because somebody didn't reorient their map to the kind of the standard way. Even for the SSR, I think there was, I don't know, I don't remember who published it, but somebody published an SSR map that people kind of started to reorient stuff to that direction. And I think the P-Noir reference genome is actually based on those directions too. But that's just so everybody's talking about the same thing in terms of describing which end of chromosomes for stuff like QTL analysis.
So this is from the RAM6 output file.
I just made these up. This is what it would look like. The numbers would probably be longer since the actual physical positions cover a greater distance than this example.
So you mean even the GeoMap still require this
Reorienting, yes. I had to reorient my. It's just a matter of, because like if we do this and we plot like centimorgans versus physical positions, ideally it should be, well, let's see if one of these markers works. Ideally it should be like this direction. So we have 0 centimorgans and 0 base pairs on this corner, and then you like go up. But if something's like oriented incorrectly, it would actually be shaped like this. And so you have 0 centimorgans, even though this is 0 base pairs. And all the reorienting does is takes this map and changes it so it's actually like this direction.
For the GeoMap, I believe if that's the case, you click, they can remove it.
Yeah, I think GeoMap can do, yeah. But you have to do each one individually, I guess what I meant.
So in that case happen, if you click the button, it will flip the
Yeah.
and then bottom.
So GeoMap will do the, I guess, I'd forgotten about that, but GeoMap will do the calculations for you, but that's what it's doing when it does that. And there's not a button for Lep-MAP3. Although I have this as part of the R script that I've written up that it'll do it
So
automatically.
you do like the day automatically minus and then add up.
Yeah, so after I've reoriented, every single chromosome is oriented this way. Before doing that, some of them would look this way and some of them would look
That's
that
right.
way, just.
Yeah, I recall GeoMap already happened that way, but if you click the button, they recalculate.
Yeah, but you would have to check which chromosomes or linkage groups you needed to reorient and which ones didn't, even in GeoMap. Okay. So now that we've renamed everything in Lep-MAP from Lep-MAP, we can start working on converting it to an RQTL object that can actually get uploaded into that. And so first we need to discuss how RQTL wants things genotyped. And for our population, most of the time it's called a cross-pollinated population. And that's because the two parents both have genotypes from different parents. So there can be at most 4 segregating alleles. And some other cross types, you might only have the A and B allele segregating if it's originating from a smaller genetic pool. So the 4-way cross is what it's called in RQTL, since there's 4 different parent alleles found within the progeny population. And so RQTL assumes that all the markers have at most 4 different alleles. Additionally, the progeny genotypes are assumed to be phased known by the program, so it's important to use phased data in RQTL. If you don't, I've never used it, but I'd assume it would alter your results. And so additionally, like for HapMap files and JoinMap files and all that stuff, we're used to seeing lettered codes. So like the A, B, C, D, or the nucleotides A, C, T, and G. What RQTL does is it uses numerical codes and not a number for a certain allele, but rather a number for a certain genotype. So the 4 traditional genotypes that we're used to seeing, the AC, BC, AD, BD, those are just all the different potential combinations from this parental cross code. Those are numbered 1 through 4. So the first allele coming from Norton and the first allele coming from Cabernet Sauvignon. If those were inherited, it would be numbered a 1, and so on for the other numbers based on which allele this is. Additionally, our QTL recognizes some more uncertain types of genotypes. For example, if the A allele is known to exist in that progeny genotype, but we're not sure whether it's a C or a D allele that has been inherited from the second parent, we can number that a 5. And so we're still able to include those genotypes, even though we don't know whether it's the 1 at AC or the 3 at AD. Similar numbers exist for the other uncertain genotypes. If the B is known, but the alternate allele is not known, it can be a 6, C would be 7, D would be 8. Additionally, the 9 through 14, which I don't use because the genotype data that comes out of Lep-MAP3 is phased already. So some of the uncertainty is already taken out, but if for some reason you weren't sure whether it was an AC genotype or a BD genotype, and these are more unlikely because it's not that you're uncertain about one allele, you're uncertain about both alleles, but you know it can only be 2 genotypes rather than the 4 genotypes. In those situations, you'd have 9 or 10. Additionally, you can describe if you know one certain genotype is not true, you can describe it that way.
So it is popular to use because like a 9 and 10 obvious so.
Yeah, I don't know what situation it would be that you would use these, because technically the 4-way cross information can be used for different types of more complicated parental crosses, not just cross-pollinated. It just means if there's it can be used if there's 4 segregating alleles. So it could be one of those like 8-way like magic populations or some things like that that have more complex parental types. Okay, so those are all the different numbered genotypes that can be used with our QTL. Essentially going from Lep-MAP to our QTL, this would be the recoding scheme. And so,
What the 12?
kind of. Okay, so in Lep-MAP, I'll go back to this screen, which is what the data file looks like after we've renamed everything. These are the genotypes given by Lep-MAP3 that have been phased. So Norton, all of the genotypes are 1, 2, because that means parent 1, parent 2, parent 1, parent 2. And the positions mean something. So the first occurring number always originates from parent 1, or grandparent 1 in the case of our parent genotypes. Grandparent 2 is in the second position. So Norton and Cabernet Sauvignon look exactly the same in these genotypes. When we look at the progeny of this, this first position means the allele inherited from Norton, which is parent 1, and the second position is the allele inherited from Cabernet Sauvignon, or parent 2. So a 2 means that allele number 2 was inherited from Norton. And so that would be the Norton grandparent 2. Whereas other genotypes, I don't see it, all of these seems to be 2. But if we look at the second position, that's always Cabernet Sauvignon. So we know in this individual, allele number 2 was inherited from Cabernet Sauvignon, parent or grandparent number 2. At these lower genotypes, we have a 2 and a 1. So instead of grandparent 2's alleles being inherited from Cabernet Sauvignon, grandparent 1 was inherited from Cabernet Sauvignon. And that's how the alleles are described coming out of Lep-MAP. And so to convert from that, so I said a 1-2 cross 1-2, so Norton, like Cabernet Sauvignon, which are the parents. We would have, let's see, the RQTL1 would be equal to a join map AC genotype and would be equal to a Lep-MAP3 genotype of 1-1.
Not AC.
AC, and I tried to include this because when I say 1-2, we can like line stuff up. Let me erase this. Oh, that one works better. So I say 1-2 cross 1. Sorry, that's kind of not where you can see. 1-2 cross 1-2 is exactly the same as A, B cross C, D. So when we look at the progeny, different genotype combinations, you got 1-1, 1-2, 2-1, 2-2. We always match like this column always goes with this parent. This column always goes with this parent. So for these,
The first one is all go to second parent.
the first, like if we lined all of these up, the first digit would always go to the first parent and the second digit always goes to the second parent. And so we can match these. This 1 is a 1 here. And so in terms, thinking about it in terms of join map formatting, 1 at the first position always means an A. Whereas a 1 at the second position always goes to the second parent and it's the first allele, and that would be a C. The 2 at the second position would mean the second allele from the second parent, and that would be a 2, which would mean a D. And so we can look at these coding schemes in terms of that. And these little, how this is written is the first number is always these numbers for the 4-way cross population type. The second code is the join map format, how it would look that way. And then this third in the equal, after the second equals,
U11, I saw in
is referencing this.
Oh,
Sorry, I guess that's
I
confusing.
think, oh, what? It's AC, not AC? No, you are saying 1-1.
Yeah, 1-1. I guess I can put spaces in there
That's it.
for readability. But so in these examples, we go through genotype number. And additionally, I've kind of left this out up until now, but what Lep-MAP does when something is uncertain, it lists that allele as a 0. So in addition to these 4 genotypes, we can also have, oops. We can also have 1, 0, 2, 0, 0, 1, 0, 2. And that would just mean the allele at this position is unknown or uncertain. And so that's what 0 means. So these would be the 8 different allele possibilities that come out of Lep-MAP3. And I've just written them down here how it would recode in each data format.
So this 1, 2, 3, this only in you just want to code it in the R or
It, like the numbers up here for this 4-way cross type, that's the only way you can put genotypic information that has 4 alleles into RQTL. It has to be in this format.
That's the only way.
Yeah,
Wonderful.
that's the only way. Any more questions about recoding it to an RQTL object? Let's see. We can look at an example of what that looks like. We can have it in here.
But this output already generates, like this usually automatically generates from the output, right? For the,
No, this has to be done manually.
Oh, really?
Yeah, like
The-
we have the, let's find it, this file. Like after we've renamed it, after we've renamed the Lep-MAP file that we just looked at, it looks like this. We have the 1s and 2s, we have the map positions, the chromosomes, which have been filled in, and the marker names. We have to go from this and convert it to numbers
5, 6, 7, 8.
and reorient everything.
We need those numbers, we need it, like for instance, the first, this one,
Yeah.
2, 2, we need it,
Convert it to
We have
the
the five
single
things.
numbers.
5, 6, 7.
Yeah.
So you say if 1, 2 equal 5, you can replace one.
Yeah, you can control F and just replace it that way. Since everything's phased, it doesn't matter.
There's a lot of room for human error.
No, you can restrict, but you.
I get drowsy and blink and I hit the wrong.
Be careful, you cannot.
So you can do it that way. I have our scripts that does all this stuff automatically.
Okay, that's-
But an alternative way would be to control F because everything's phased. So a 1, 2 is different than a 2, 1. You don't have to consider more than one exact.
5,
genotype.
6, 7, 8, what the 0 represent?
Uncertain. I'll see if I can find any 0. Okay, so for example, a lot of times the zeros come at positions on the chromosome where there's been like a crossover event. And so it's not exactly 100% sure how to phase that, like right at the junction between the two different phases. And so it fairly often will put like a couple of zeros right there because it's not 100% sure whether that crossover event occurred at this marker or the marker next to it, but it's sure that all of these markers downstream or all of these markers upstream, which haplotype they belong to. And so like here, we have 1, 1 above. Okay, let me reorient myself quickly. So the columns are the individuals. Going down the column would be looking at along the chromosome. So going to that 0, 1, we have 1, 2. These are all 1, 2s as they should be since it's phased and you'd expect that like haplotype block to be the same. And then down here, it's all 1, 1. But at the switch between the 1, 2 and the 1, 1, we have a couple of 1 zeros. So that would mean there was a crossover event from the Cabernet Sauvignon allele where these individuals inherited the allele from Cabernet Sauvignon grandparent 2. And these individuals inherited the allele from Cabernet Sauvignon and grandparent 1. And these ones, they're unsure about which Cabernet Sauvignon allele was inherited because that's like right at the junction of the crossover event.
So you will give 0, still 5, 6, 7.
I leave the uncertain haplotypes because I would rather input it as uncertain data if Lep-MAP truly is uncertain rather than it make its best guess. Because this is still like informative for mapping purposes. And then you're not,
So you're gonna assign 0 or what number?
the zeros are represented in the RQTL genotypes. That's like what I was talking about for these. Another way to look at this would be like A question mark, B question mark. And these, the C and D would be question mark C, question mark D, where in the Lep-MAP3 code, the question marks would be the zeros. So we know the first allele potentially, or we know the second allele, but we don't know both of the alleles for that genotype.
We in our script only allow single digit, right?
The R QTL four-way cross object only accepts well, technically it could be a single digit, but for our purposes, we'll only be using 1 through 8. So yes, a single digit
If that
on
case-
our data
So
files.
in that case, uncertain, what number should assign?
The ones with one uncertain allele would be these 5 through 8. If both of the alleles are certain, it would be one of the 1 through 4s.
Okay.
And how our QTL, how their files describe it is AC or AD, because the 0 could potentially, like obviously there's only 2 options from each parent. So since we know it's an A at the Norton position or the Norton allele, it could either be a C or a D. So the genotypes AC or AD would be the only 2 options if the first allele was known to be a 1. Any other questions? Otherwise, in addition to the number scheme, that always stays the same for our populations since they're always the 4-way cross containing 4 alleles. There are some different options regarding input formats into our QTL as far as how you organize the genotype information, the phenotype information, and the map positions. And these are all the different options that are accepted. These first 1, 2, 3, these first 4 are essentially the same. Stuff can just be oriented a little bit different. I always use the CSV because that's how I set up my script to write it out. And it's easy just to keep the name designation that I use short rather than using some of these longer ones. And I'll show you what that looks like in a minute. These other formats are useful, like when we were using JoinMap, we could input it as a JoinMap style file with a few minor alterations. And that might be why, Lillian, you don't remember recoding some of the earlier JoinMap stuff, because if we do input it this way, it does accept the A, B, C, D cross scheme if you use this input file type.
Would that take it or not?
It takes it, it's a lot harder to use this format because there's a lot less examples of how to format stuff. And especially now that we include the like GBS and RampSeq without recoding those into the ABCD cross scheme, it's easier to use these CSV options. And so these first 4 options, you have your like original file type, which is the CSV, and some of these others are just like whether it's rotated or transposed would be another way to phrase that. And then these 2, you can have separate files for genotypes and phenotypes.
They are also the same purpose, right?
Yeah, they all serve the same purpose. It's just a different way of organizing stuff. So this is an example. I'll delete some of this stuff. This is an example of an RQTL CSV file format. And so in the first columns, you can have 1 column, 2 column, 10 columns, 20 columns, however many you want for phenotypes. But the first columns are always the phenotypes. And so this is cold hardiness data. So I have the dates, the month dates. So January 2021, February 2021. Following the phenotype columns, you start your genotype information and the map data. So in the first row,
What's the first column?
this first column, the A and the B, those are the phenotypes that correspond with this population of data. Another,
How come you have 2 column phenotype?
because I have 2 phenotypes. You can input as many phenotypes as you want
Okay.
to the beginning of this. It just has to be,
At the
it just has to
beginning.
match the genotypes, but you can have as many as you want.
So you combine your
Yeah, like I had just deleted a bunch, but this is actually what how many phenotype columns my file had. I had A through L were all phenotype
So
columns.
they can accommodate as many as you want.
Yep,
long
as many
put
as
it
you
in
want.
Order.
Yeah, as long as these are all ordered, which when you input it, you don't actually have the individual names in the file. I usually save a copy. Let me open. I usually save a copy that does have the names in it just so I can double check stuff. I just need to open one that has a RQTL with NCRCS names. Okay, so this is a preliminary file that I have. These are all of the individual names, and you can use as many phenotypes as you want, just as long as all of the Norton Cross Cabernet Sauvignon individual number 1 is in the same row.
This is the format name, like this is the genome and this is the marker name, or you can transform the one or the other way.
You can transform it the other way. That is what I was getting
way
into
more?
with these different formats. If you rotate them, you have to use like CSVR or CSVS if you still, because you can have the genotype and phenotype data in separate files if you want to. You just have to make sure everything is lined up correctly.
So you mean the simple way, like this is genotype and this is the marker. That's the
Yeah.
marker.
So to describe this, just to describe this a little further, the phenotypes are all of the first columns, and then as we get into the actual genotyping information, which is all of this data, the first row is all of the marker names. And so these are 14 and so on. The second row is the chromosome number. So it's 14 since all of our markers belong to chromosome 14. And then the third row, I'll zoom in. The third row is the map positions in centimorgans.
So this file you made from the previous file you transform.
Yep, I basically, all of this is just the Lep-MAP kind of like flipped. And then this stuff gets added onto the side. And so after the first three the first 3 rows don't correspond to any phenotype information. And so the second and third rows preceding the genotype information need to be left blank. They need to not have any data in them. Otherwise, you won't be able to upload this file into RQTL. And then below that, we actually have the genotype information. So the 1s, 2s, 3s, 4s, which you can see that most of these are 1s and 2s and 3s and 4s. And there's less of the 5, 6, 7, and 8 because those are less, the uncertain genotypes are less prevalent.
So this is all the markers. So all the markers are certain. You look at only 1, 2.
Here, yeah, it seems like all of them are certain. I'll Control F for a 5. There are some 5s.
Oh.
And like before, how we looked down the column to follow the individual, this would be across the row to follow the individual. So like these, the haplotype is genotype 3, and then it switches to 1 down this way. And between those, there's a 5. And the 5 is one of those uncertain genotypes.
So even those things you still keep it, we still can.
You can still use it, it's still informative.
Unless the whole markers are really uncertain.
Yeah, if it's truly uncertain, Lep-MAP will put it as 0, 0. I don't know if I've ever seen any 0, 0s. Because it can use at least phase like 1/2 of the data. Okay, we might wrap that up for this week since it's 9:30, unless you guys have any more questions about reformatting it into RQTL. This is RQTL CSV file format. And if you are curious about, let's see, RQTL. If you are curious about the other file types, the website rqtl.org has examples of that stuff under sample data. So they have CSV, CSVR, CSVS, CSVRS, the map maker, map manager, QTL cartographer.
I'm just wondering how much time you put on this in order to become so efficient. And don't forget it, you are, well, I don't want to use just, but you are a master student.
I don't know.
This is more like, well, you've been to the, how you call that, the Bible gym meeting, right? This is the postdoc people doing this, not a master student doing this. So
I
I'm
don't know.
wondering
No, I
how
think the
much time.
most impressive is because she is not computer science background. I mean,
Right.
for the computer science background, they can take it easy, but for the agriculture kids, normally, everybody has no background story.
Well, a lot of it, like our QTL does a good job with examples. Like this website has also, like it has examples for all of this. It has several pages of like tutorials on how to use stuff.
She went to read.
Yeah, I'm really, dang, she keep you here.
No, she really
But,
go
yeah.
into detail because,
See,
yeah,
because this is, well, I mean, better than most of the postdoc for now, actually, on the genotyping side. That's what I mean.
because only few people do the genotyping like
Not that many
AV, and then
people.
few. The rest of them, they actually don't do this either.
Yeah.
Yeah.
We don't have anybody else to do that here, so
No, I think, I'm sure like Ava, I mean, what the,
80,
and then another guy and do the berry one.
the very, oh, the Noam.
I'm sure he probably had to start to do it as well,
Mm-hmm.
just because, generally speaking, though these things only AV doing.
Mhm.
I don't think all the postdoc being releasing it.
Yeah, it sounded like he was making most of the maps at least.
No,
I don't know
because
about
they
this stuff.
separate their job, we have been finally find out, like, so we may not touch this thing either.
Yeah.
I mean, of course, all of them probably like to learn for the long term, future use. But I don't think that all of them are able to do this portion of it. But I don't, now AV is gone, so I don't know how.
I don't know who's doing that.
See, like, Sarai did 2-3 years of